Hello student, to the lecture number 3 and of wave optics. So today we are going to study the concept of wave and wave equation. So in the last class, in fact, we have already discussed about the wave equation and discuss about the form of the wave. Let me do that once again. So today we have lecture number 3 and let me draw what you had the last day. Suppose for a fixed coordinate system, I have a disturbance like this, which we call wave in O prime frame. Along this direction, say this is x, and the disturbance amplitude is along this direction, y direction, and we write y as a function of x. Now, if this wave moves over the time, then at some point, if this is a fixed frame and O prime is a frame that is moving with the wave, so the wave is now will be at this position. Whatever the point we have here, from here to here, this length, if it is x prime, since the frame O prime frame is moving with the same velocity that of the wave, this length will remain x prime. However, if the wave is moving at some velocity v, then after time t, this length will be simply v into t. And from this fixed coordinate, this particular point, I can write this particular point, the coordinate, as x. So we have a relationship between x, t and x prime, something like this. X prime will be equal to x minus vt. In the last class we have done this. If the wave is moving in the forward direction, it will be like this. If it is moving in the opposite direction, then this sign will be, this minus sign will be plus sign before v. So here we have a plus sign. But the thing is, the function y prime, which was initially, say this is in the prime frame, I should write y prime. So y prime, this is essentially function of x prime, and I can write this as a function of x minus vt. The shape of the wave remain conserved during this process, then always we have a functional form whose argument is x minus vt that gives us the feeling that this disturbance or wave is moving along x direction with a velocity v. So we give some examples like y equal to a sine of, this is a very standard form we are going to use later, k x minus vt, or y equal to something like an amplitude x plus vt square, or y equal to some amplitude e to the power of x minus vt with a factor k here, square also. So all these are function, I can write in general these as a function of x plus minus vt. So all of them will in principle represent a wave that is propagating along x direction. Now, since we have this expression from here, we're going to see that if we have a disturbance that is propagating, then it will follow certain equation which we call the wave equation, which is very important, because this wave equation will going to appear when we solve the Maxwell's equation, when we try to regenerate how the electromagnetic wave is moving through Maxwell's equation, then we are going to encounter this kind of equation. So beforehand we need to know what is the wave equation. So let me derive that first. Wave equation. So y, we already see it is a function of x prime in the previous example, where x prime is x minus plus vt. It can be minus vt, it can be plus vt, depending on the wave is moving in the forward direction or in the backward direction. Now from that we can have few information, like if I make a derivative with respect to partial derivative with respect to x of this parameter x prime, we will going to get 1, and if we do that x prime as a function of derivative as a function of t with a function t, then we are going to get plus minus v. Because x prime is a function of in general, so I can write x prime here is a function of x and t. Okay. So now I have a functional form like y should be a function of x prime in this particular form, which is given here. Then I can write del y del x is equal to del f del x prime del x prime del x. Y is a function of x and t, but it is equal to f of function of x prime. So using simply a chain rule, I can have this. So this is essentially del f del x prime, because del x prime del x is equal to 1 with this transformation, whatever the transformation we have. Similarly, if we go a second order derivative of this quantity with respect to x, we can have del x, and then dy dx I can replace as del f del x prime, which is del x prime del f del x prime and del x prime del x. Again, this quantity is 1, so we will have something like del 2f del x prime square, which is equal to d2y dx square. Now we go, so this is my one result. Another thing I can do by making a time derivative, because another variable time is there. So dy dt is essentially dx prime, sorry, so I need to erase this. So it was okay actually. Dx prime of f and then dx prime dt. So dx prime dt, already I figured out it is plus or minus v. So it is plus minus v, which is a constant quantity, and then del f del x prime. If I go a second order derivative like we did in the previous case, it should be a similar kind of thing where I can write plus minus v del x prime of this quantity del f del x prime, and then using the chain rule del x prime del t. Del x prime del t again plus minus v. So plus minus v multiplied by plus minus v, we have v square del 2f del x prime. So I can have also the value of the second order derivative, but if I compare equation 1 and equation 2, then from this equation and equation 2, we can readily have one expression, which is one differential equation, which is y dx square is equal to 1 by v square d2y dt square. So this is the expression we have, this is the differential equation we have, and if I write this is 3, so this equation 3 must be satisfied by this particular functional form that we have, and this basically, so you can see that the y having the form f x plus minus vt, a general solution of this differential equation that's derived. So whatever the form you have, if you have whatever the functional form you have, but if x plus minus vt is there in the argument, then always this kind of function should be a solution of this differential equation that is shown in equation 3. So that means that equation 3 is a governing equation of this propagating wave, and that's why this equation 3 is called the wave equation. This is wave equation. But note that this wave equation is done only for 1D. That means if the wave is moving in one dimensional way, in one dimension coordinate system, suppose it is moving in one dimension along x direction, then this wave defined by the variable y should be following this wave equation that we just derived. In 3 dimension, however, in 3D, this wave equation takes the form in this way. Where psi represents the wave, and in general that is a function of r, vector r and t. And del square is a Laplacian operator. Depending on the system, we can write del square operator, and this is the expression for, this is the wave equation for 3-dimensional wave. With this note, now we like to show in the next case that what are the most general kind of solution one can expect for example, in 1D differential 1D wave equation. In 1D wave equation we have, let me write it once again, d2 dx square is equal to 1 by v square d2y dt square. That is my 1D wave equation, and this 1D wave equation have a solution of the form, as I mentioned, that it should have a solution of the form like this. So let us take a particular form which is a very well known form, and that is called the harmonic wave. Harmonic function that represent harmonic wave. So what is the harmonic wave? X should be a function of x and t, and I should have the form of the wave or the solution of this wave equation as sine or cosine function. So let us consider this as a sine function, k x plus minus vt, and this. Or we can have a solution as a harmonic wave as a amplitude cos of k x plus minus vt. Okay, so if we look carefully to this equation, we can find that we have a multiplier every time k here, and that we have to do because to match the dimensionality, because sine and we have some argument, and this argument has to be dimensionless. X plus minus vt is a quantity and that has a dimension of length. So we should have a multiplier here whose dimension has to be 1 by length, so that k multiplied by this quantity should have dimensionless. This thing should be dimensionless. So the dimension of k is 1 by length, that we can check easily from here. Later we are going to discuss what is k and all these things here only. Now at y, if I find what happened at t equal to 0, then we can see that y is a function of x only, and we have something like a of sine of kx, because t is 0, so we have a sine of kx. So k here generally greater than 0, and it has a name, we call this as propagation constant. This is propagation constant, and dimension of k we already mentioned that it should be 1 by length in order to make this argument of sine dimensionless. Now if I plot these things, we can go to next slide. If I plot this function, sine function, this is my y, then we will going to get a function like this. If I go beyond, it should be like this. Okay, so over the t, if I plot, it will be a sine function for a constant x, and for a constant t also we are going to get a similar kind of expression, similar kind of form, similar kind of figure. Now for constant x, I have 2 points here to here, and for constant t also I have 2 points here to here, which are in same phase, So the length, the distance between two points having the same phase is known as lambda, where lambda is the wavelength. So this is the spatial period we have. So essentially, the spatial period is lambda, which is the distance between the points having same phase. And this we called, already mentioned, this we called wavelength. So that means if we have the function xt some value, then this value I'm going to get equal if I move this spatial period. That means if I move from x to x plus or minus lambda, then I'm going to get the same point. For example, here from here to here I'm going to get same point. Also I have a same phase point here and here. The distance here is also lambda. So if I have the amplitude here, then if I move by the length of spatial period lambda, which is wavelength here, then I'm going to get the same point. So if that is the case, so I can write the equation like a sine of k and x plus lambda, say, minus vt, that is the equation of a propagating wave, that is equal to a sine k x minus vt. The same point I'll get. So if I tally these two equations, then readily we can see that this value is k multiplied by lambda should be 2 pi, because I'm going to get the same. So this is equal to a of sine of k x minus vt plus 2 pi. You can have also 2 pi multiplied by some integer, but let us take with this the smallest increment, so that I will going to get the same point, same consecutive points. From here one can find the amplitude of the k. K is 2 pi divided by the spatial period lambda, and that is an important expression for optics as well. When we deal with the electromagnetic wave that is propagating in a medium, then we always mention about the propagation constant, and this propagation constant is defined by this 2 pi by lambda in free space. In the medium, however, there is a refractive index. You need to multiply a refractive index n here to make this complete. Well, like the spatial period, we can also have a temporal period. So let me draw it once again. So I have y function of x and t. This is harmonic wave. This is a property of the harmonic wave, and over the time, for x equal to constant, that means for a given x, it is vibrating, and again we will going to get 2 points that are having the same phase. When the wave is moving in time domain, then we call these two consecutive points having the same phase, the distance between the 2 points in time domain is called the temporal period. We write it as tau. Like previous case, I have x t that is equal to y x t plus minus tau. I'm going to get the same function. So I can have a sine k x minus vt, and then that is equal to a sine k x minus v t, say, plus tau. So from these two equations, again I can have an equation k multiplied by v multiplied by tau has to be 2 pi, like in the previous case. And from here I can have tau to be 2 pi divided by v multiplied by k. But we already know that the value of the k is 2 pi divided by lambda. So here if I put this value, I'm going to get simply lambda divided by v. So tau is lambda divided by v, that is the amount of temporal period one have. If the spatial period is known, then the spatial period, from the spatial period we can have the temporal period through the velocity of this wave. Now 1 by tau is equal to nu, and that quantity is called temporal frequency. Temporal frequency, that is a quantity which is also important. Temporal frequency. There are also one important quantity that we are going to use in our calculations, and that is omega, which is 2 pi divided by tau, or 2 pi multiplied by the temporal frequency nu. This quantity is known as angular frequency. So once we know all this harmonic wave, the nature of the harmonic wave, then we can write also the form of the harmonic wave as a complex function, which is very useful, and we will going to use that in our course several places. So let me introduce here. So harmonic wave as complex function. Complex function. So we have y tilde, that is the notation normally we use. So let me erase this part. So we have y tilde, that is equal to a e to the power of I kx minus omega t. Now we know all the values, what is k, what is omega, and now we are allowed to write the expression like this. So y is basically, I can write as a real part of y tilde, and that is A cos kx minus omega t. If we want to write the sine, this is a cosine form of the harmonic wave. If I write the harmonic wave in sine form, then I can also write this, and then you need to write that is the imaginary part of y tilde, and that is a sine of kx minus omega t, where k is the propagation constant defined by 2 pi by lambda, and omega is the angular frequency defined by 2 pi by tau, and omega divided by k, that quantity is 2 pi divided by tau multiplied by lambda divided by 2 pi, or it is lambda divided by tau, which is essentially represents the velocity of this wave. So with this notation, we can write down the harmonic wave in a complex fashion, and from that we can extract the real and imaginary part as cosine and sine function. And inside the cosine and sine function, I have two important terms. One is k, which is the propagation constant defined by 2 pi by lambda, and also the angular frequency, which is defined by 2 pi by tau. Lambda is a spatial period, and tau is a temporal period of a harmonic wave, and omega and k are also related in this way, so that at the end of the day we find that omega divided by k is the velocity at which the wave is moving. So with this note, I would like to conclude here. In the next class we will learn more about the wave nature, different kind of waves in different system, plane wave, then spherical wave, etc. And then we do all the related mathematics in detail, so that you can understand the physical concept as well as the background mathematics. With this note, I like to conclude here. Thank you very much for your attention. See you in the next class.